Alright, so let's expand our knowledge a little bit as far as D and L notation goes, or R and S, depending on your point of perspective, right? So here we see a molecule, and this molecule is a little bit longer carbon chain than our previous examples that we've been working with. We kind of stuck with a 3-carbon chain that we've been using to discuss stereochemistry all of this time. And now I see this structure and I see this molecule, and it's got more carbons on it, and there's more OH groups on it, and I'm required to basically provide you with a D or L notation. So how do we do this? Well, first, let's talk about the number of chiral carbons that we have on this molecule. Okay, so let's start up at the top, and let's just put a box around all of our chiral carbons. Up at the top, we basically see a carbon that doesn't have 4 bonds to 4 different groups, right? It's a double bond to an oxygen. So that is not a chiral carbon. So we go to the next one. This carbon here has an OH group, has a hydrogen group, has the aldehyde group, and then it has this CHOH, CHOH, CH2OH group. This is a chiral carbon, so that carbon has a R and it has an S. It's either or. We've got to figure out which one it is. The next carbon in line, guess what? It's a chiral carbon as well. Here we see a hydrogen and we see an OH group. And then at the top we see CHOH with the aldehyde, and then down below we see CHOH with the CH2OH group. You have to take the groups in the entirety. You can't just say, well, that's a carbon with an H and an OH on it, and this is a carbon with an H and an OH on it, so this carbon, well, it's got 2 of the same groups. No. That's not what we're doing. You've got to take the entire group as a whole. So that means this carbon and everything else that follows with it, and this carbon and everything else that follows with it as well. So this is a chiral carbon, which means that has a R and an S or a D and an L associated with it. Then we take a look at the carbon down here below. Well, guess what? That's a chiral carbon as well. We have an H and an OH, then we have this CHOH, CHOH, then the aldehyde group at the top, and then down below we have just the CH2OH group. So this is a chiral carbon as well as the other 2. Okay, so we've got 3 chiral carbons here. That means that this has a R and S form, this one has a R and S form, and this one has a R and an S form. That means all of the combinations up above can exist. A RRR, SSS, RSS, RRS, SSR, SRS. Any of the above combinations can exist as far as a stereoisomer is concerned with the sugar. But here's the lifesaver. You can wipe the sweat beads from your forehead, because we are not going to go into, well, draw all of the stereoisomers that this compound could have, because as you can see, there's quite a number of them. So we just really still want to stick with, is this compound a D sugar or is this compound an L sugar? Is it an R sugar? Is it an S sugar? What is it? And there is a trick. And the trick is look at the position of the OH group, just like in the previous video. But which OH group, you're saying? There's 3 of them here. There's one kind of at the top and one in the middle and one at the bottom. Which one should I focus on? Well, if you've got a sugar or a molecule like this in a Fischer projection, and you're required to determine if it's R, S, D, or L, the number one thing that you do is look at the OH group that is last. So the OH group that's important here is right there. Okay, that's the OH group that I'm after. All the other OH groups we're going to ignore. We're going to pretend like those aren't important. We're going to pretend like I don't have to bring those into consideration. We just assume that they're there. We know that they're chiral. We know that they have kind of R and S forms. But if I want to label the sugar as a whole, as a D or a L, I'll look at the very last OH group in the chain, in the backbone. And this OH group in the backbone, don't count this one, right? This one's the tail. And don't count anything up here if it's there, because that's the head. You look at the backbone, the OH groups that go in the vertical or the horizontal position, left and right. This OH group is to the right, and just like before, that means this is a R sugar or this is a D sugar. So number one, you look at the OH group that's last. Number two, if it's on the right hand side, then this gives you the R or the D version, and if it's on the left hand side, it gives you the S or the L version. So that is the way that we determine these carbohydrates that maybe have more complicated structures as far as these examples are going to be concerned. Now, number three, we have to put a big star here. And this thing is going to say this works only if the aldehyde group or the ketone group is at the top and the CH2OH group is at the bottom. That is the only way that this will work every single time. So, you know, if you go back and you rewatch some of these videos, you keep hearing me say, well, if you're given the opportunity, or if it will allow you to draw the structure this way. You know, that's very important because the orientation of all of these other groups are going to be important, just like the orientation of the OH group is important. So what that means is that if the aldehyde or ketone group is not up at the top and the CH2OH group is not at the bottom, then this little trick will not work for you. And my advice at that time is to bring out a model kit and structure the model based on how the Fischer projection is drawn. You've got to remember top and bottom point away and the sides point towards you. So take your model kit, take the carbon out of it, and then you will have one that will kind of be pointed away, top and bottom, and then two of these on each side will be pointed up. Well, the ones that point up, you're going to put a hydrogen on it, and you're going to put an OH group on it. The ones that point away from you, I'll just draw these dotted lines. That's a CH2 group and a aldehyde or ketone group. That points away. So once you structure that model the proper way, then you can kind of take that model, twist and turn it, and figure out whether you have the RS, D, or L version. Alright? So it only works if the CH2 group is on the bottom and the aldehyde or ketone group is up at the top. So for instance, let me give you an example where it doesn't work. Right? So let's see one of those. Let's say that we have a structure that looks something like this. A C double bond O with an H here. And then let's draw a Fischer projection. So it looks something like this. We'll put a hydrogen down here below. We'll put the OH group that's there. And we'll put a CH2OH group that's over here. Alright, your shortcut will not work with this example. And again, the reason is because the aldehyde is up at the top, but your CH2OH group is not down below. And that's an issue, that's a problem, right? It doesn't meet the template. So I can't shortcut this method, and I can't say, oh, the OH group is on the right here, so this is the R form. I mean, maybe if I'm lucky, I'll get it correct. But I really want to double check and make sure that I fully understand the stereochemistry here, because that shortcut will not work, and that's going to cost you points on a test and an assignment if that's what you do. Alright, so let's take a look at how we can maybe do this without a model kit. Well, keep in mind that this is my chiral carbon. So my chiral carbon's right here, and I've got one that points up, one that points to the side, one that kind of points forward, and one that kind of points backward. If I can kind of change this Fischer into a perspective, then I maybe could get the stereochemistry from it, right? The easiest way to do that is the model kit. The hardest way to do it is by using a sheet of paper and a pencil like we're getting ready to do right now. So you got to keep in mind, first off, here we see the chiral carbon. This OH group is pointed toward me, and this CH2OH group is pointed toward me. That's what the Fischer projection means. The aldehyde group, that's pointed away, and the hydrogen, that's pointed away. Okay, well that's good news, because the hydrogen is pointed away from me. And that means in the priority scheme, that's traditionally where we would see these hydrogens. We would see these hydrogens basically pointing away. And if that can happen, then that's good, because that's what we want. Okay, so that means that in this perspective formula, one of these dash bonds, that could be my hydrogen. And now I need to take a look at how the other three groups are going to be oriented for each other, right? So one of them is an OH group, and one of them is a CH2OH group, and that is pointed toward me. Okay, well, the groups that point toward me, that's not a big of a deal as the one that goes up at the top, right? We want to know which one of these is the highest priority group. So in my Fischer projection, what was the Fischer projection? So let me clean this back up and change it back to a Fischer. I don't want you to get confused with the whole Fischer versus perspective, right? We want to kind of keep track of what we're doing here. So this is the Fischer projection. Our highest ranked group is group number 1, and that's here, right? Group number 1. So if you don't have a model kit and you need to figure out if this is R or this is S, you can kind of convert that over to a perspective formula, and that's what we're doing now. There's some short tricks that we can do here as well. Number 1, you rank the groups, just like we did before. So this is high priority, this will come in second, this will come in third, and this will come in fourth. So I now rank them. And then you just draw an arrow like you'd normally do with perspective formula. You draw an arrow from the group with the highest priority to the groups with the next highest priority, and so on. So the arrow here is going to go from group number 1, and then group number 2, and then group number 3, and then group number 4. This is counterclockwise. Counterclockwise means that this is a S configuration. However, this only works if your lowest group priority is down at the bottom. Alright, so this is where hydrogen is at the bottom instead of my CH2OH group. And hydrogen's at the bottom, it's got the lowest group number. And if it's at the bottom, then whatever rotation that we see here, that is directly related. So this would be the S form or the L form. And if I have to convert that over to a perspective formula, then I can do that. My OH group is top priority, it goes up here. The next one in line is the C double bond OH. So that's the one that actually is going to go here at this solid wedge. And then the CH2OH is going to go here. And this gives me the S rotation, just like the Fischer projection does. So again, we've talked about this before. This wasn't a new concept. Go back to the stereochemistry lecture or the chapter in your text. Look, it will say Fischer projection, and it will walk you through on how to do this Fischer projection if the structure and the template doesn't quite match the way that we want it. So number 1, rank the groups. Number 2, draw the arrows. Number 3, if the hydrogen is at the bottom, that rotation is just like you've drawn it on the sheet of paper. If it's not, it's backward. But go back to the textbook, review that material, and you'll be okay.